Welcome back to Pratik Academy. In this video, we will study equivalence between two important statements of second law of thermodynamics, that is Kelvin Planck statement and second important one statement is Clausius statement. In this video, we will study equivalence between these two statements. Okay, we know that both these two statements are having negative approach. We have discussed this part in last video. This is also again having negative approach. Okay, this statement, Kelvin Planck statement, it is related to heat engine. Okay, and this Clausius statement is related to one device which will transfer heat from low temperature to high temperature. That means it can be refrigerator or heat pump, okay, depending upon purposes or desired purposes. Okay. According to Kelvin Planck statement, it is impossible to construct a engine working between two thermal reservoirs and whose sole purpose is to transfer all the heat supplied from high temperature reservoir into equivalent work, that is W is equal to QH, is not possible. Then we have derived or find out possible outcome. Possible device is some heat is rejected always to environment and output work is QH minus QL. This is our heat engine working according to Kelvin Planck statement. In Clausius statement, this statement states that it is impossible. What is impossible? To transfer heat from low temperature to high temperature. Suppose QL is the heat transferred from low temperature, QH is the heat supplied to high temperature, and if work done or external work done is zero, then it is impossible. Then what is possible? Then we have to supply some non-zero work here, and that is coming to be QH minus QL according to first law of thermodynamics. So at first glance, these two statements are different from each other. It is applicable for heat engine, it is applicable for refrigerator or heat pump. So at first glance, we will not find any equivalence or similarity between these two statements, but there is a one similarity or equivalence. That means if any one of this state or if Kelvin Planck statement false, then a system based upon false Kelvin Planck statement will result in false Clausius statement, or if a system based on false Clausius statement, it will finally result in false Kelvin Planck statement. Okay, so this is the equivalence. That means in roughly यहाँ हमको शक्तिमान ही गंगाधर है ये प्रूव करना है. Then how to prove? Let's start. There are two ways. Then we will discuss only one way in this video, and another way we will discuss in next part of this video, or if possible I will come or I will complete that part in this video also. So first take one heat engine and one refrigerator obeying Kelvin Planck's law and Clausius law respectively. So first we take one heat engine here which is working between two temperature reservoirs, high temperature and low temperature. So it is a heat engine. It takes QH amount of heat from high temperature, rejects some heat to environment or low temperature reservoir, and result and remaining is converted into work done here, QH minus QL. So this heat engine is possible according to Kelvin Planck's law or statement. Then again we will take one refrigerator which is working between same temperature range and obeying our Clausius law or statement. That is, we will take refrigerator which is transferring QL amount of heat from same TL temperature to higher temperature by using some work here. Here external work is provided, so heat is transferred, or it is possible to transfer heat from low temperature to high temperature here, QH. Here we denote it as QL1, QH1, QL2, QH2. This is a engine work, WE. This is the required refrigerator work. So both these devices, heat engine is possible according to Kelvin Planck's law, and this refrigerator is again possible. Now this is the first step. First step is to take one engine and one refrigerator which is obeying corresponding laws or statements. Then in second step we will make heat engine not to follow Kelvin Planck statement. Kelvin Planck's statement. Okay, that means this is the we are taking a heat engine which will converting all the heat supplied into equivalent work. That means QH1 is equal to WE here. So this is the engine. It is not following law, but our refrigerator is following law, and here our refrigerator is required some input work, and here we are getting some output work. So we are using this engine to drive refrigerator. Okay, the third step, make heat engine or use heat engine to drive refrigerator. Okay, then here we get QH1 engine E. This is refrigerator. Okay. WE is the work supplied. We don't require any WR here. Then this is the refrigerator. Then output is QH2 here. Heat taken from low temperature is QL2. Then temperature ranges are TL, TH. Now this is the combined system. Now fourth important step is to apply boundary conditions. This is the important step, apply boundary conditions. Okay, here apply boundary condition now. So here QH1 heat is coming, QH2 heat is outgoing, QL2 heat is coming, and within this there is a WE. Okay, now we know that heat and work are transient forms of energy and that only experienced at the boundary conditions. So there is no any work which is crossing the boundaries. So we are not considering this work here. Then again, if you modify or simplify this, we get here TH, TL, TL, TH. So if we combine this, let's call it is again transferring heat. So we'll call this a combined refrigerator. Again, incoming heat is QH1, and at QH2 here, if you consider only, if you take this part and consider this part only, then here QH2 is actually equal to WE plus QL2 here. Again, QE is equal to QH1. So QH2 is equal to QH1 plus QL2. Okay, I hope you will understand this. QH2 is equal to QH1 plus QL2. Now putting values here, this is the QH1 incoming, outgoing heat is QH1 plus QL2. Again here from lower side we get QL2 here. Now incoming heat positive, outgoing heat negative, QH1 cancel out. Again if you simplify this diagram, we get here QL2 at higher side or higher temperature side, this is the R. Then QL2 lower temperature side to high temperature. That means we are using a engine which is not obeying Kelvin Planck statement to drive one refrigerator, and then we get finally this type of refrigerator. In this refrigerator there is no any external work. Okay, no any external work. External work is zero. Here work is within boundary, not crossing boundary. So external work is zero. Though external work is zero, heat is transferring. QL2 amount of heat is transferring from TL temperature to higher temperature, lower temperature to higher temperature. Again, this is impossible on. Okay, this is impossible according to Clausius statement. That means if we make heat engine not to follow Kelvin Planck's statement, then and use this engine in our system, then our Clausius statement is also false. So this is the equivalence. One statement false, another will be ultimately false. So this is the equivalence, or this proves equivalence between Kelvin Planck statement and Clausius statement. This is the one way. Here we are taking engine which is not following law, but refrigerator following law. There is another way to prove this equivalence. In that way, we will take engine to follow law, but refrigerator not to follow law. Okay. In up to this part of video, we have taken first engine not to follow law, Kelvin Planck's law, and ultimately we get refrigerator which is not following law. That means if Kelvin Planck's law is disturbed, our Clausius law is also disturbed. Now we are making another approach to prove equivalence, in which we will take a refrigerator not to follow law, and if we use this refrigerator to combine with engine, again engine will not our Kelvin Planck's law. So initially, as previous first step, we will take one engine, one refrigerator which are following their respective laws. Then here we make refrigerator not to follow Clausius statement. In last part we make engine not to follow Kelvin Planck statement, but for another approach or second approach we are making refrigerator not to follow our Clausius statement. Then what will happen? Then we will get, or we will have a refrigerator which is transferring heat from lower temperature to higher temperature without using any external work. It means here QH2 is again equal to QL2 because there is no any work added here. Okay, now here we are getting some heat at higher temperature, and here we required some heat at high temperature to supply for engine. So use this heat to drive this heat engine. Then what will happen? Third step is use refrigerator to supply heat for engine or heat engine. This is the third and important step. In previous one we use heat engine to supply work for refrigerator. Okay. Both are working in same temperature ranges, so TL and TH both are same for both the devices. Here this is the refrigerator, okay, having zero work, so not required to show QL2. Again same heat is transferred to high temperature side, and here this heat is again coming to supply here. Okay, so initially it is QH1, now we are adding QL2 heat which is removed from low temperature and added here, and by taking this heat some part, it means QL1 amount of heat is rejected to surrounding and remaining is used to work. Now for work, here we have QH1 plus QL2 minus QL1 amount of heat. Okay. QL1 plus QHL2, this is the supplied heat minus rejected heat. Now as previous, apply boundary condition. Apply boundary conditions across the system, then we will get here refrigerator, engine. Okay. This work is output, so output work is QH1 plus QL2 minus QL1. Okay, then this is the heat supplied, QL2, heat rejected, QL1, and this is again QL2. Here get QH1 plus QL2. Now apply boundaries. Okay. Now here if you look here, work done is crossing this boundary. In previous one, work done was internal part, so we have not considered. Here work done is crossing boundary. Again heat transfers are also crossing boundaries. Then if we simplify this, we'll get here again by supplying heat we are getting work output, so we'll make this the one engine. equivalent engine. Okay, for simplicity I write W part here. W is equal to here QH1 plus QL2 minus QL1. Here is the work output. Heat supplied, here it is QH1, just the QH1 plus QL2, heat removed from system, QL2 at higher temperature, QL2 is the heat supplied at lower temperature, and QL1 is the heat rejected. Now incoming heat positive, outgoing heat negative. So at higher side we can cancel this positive term with this negative term. Then net heat input or net heat supplied to engine, if you consider net heat supplied is here QH1, okay, QL2 is input, so it is, sorry, QL2 is input, so it is plus, and QL1 is out, leaving from boundary, so QL1 is minus, and work output here we get is W is equal to QH1 plus QL2 minus QL1. Now if you look at this, then here we got one engine which is converting all the heat supplied into work, QH1 QL2 QH1 QL2 minus QL1 minus QL1. So this engine is having 100% efficiency, and this engine is again not possible according to Clausius statement. So here we first break this Clausius statement and ultimately got a engine which is also breaking or not following Clausius statement. So in this another way also we have proved equivalence between Kelvin Planck's and Clausius statement. Thank you for watching. If you like this video, please subscribe our channel.